Okay, so this is 2.6, solving absolute value inequalities. Solving absolute value inequalities. Start out with something like this. Just a little quick review on the absolute value. Remember, the absolute value of x is equal to 2. The definition of absolute value, as you recall, is the distance from 0 on a number line. So that means x could be 2, because if I take the absolute value of 2, it's a positive 2. If I take the absolute value of a negative 2, the absolute value of a negative number is a positive number, so it's a positive 2. 2 would equal 2. So my solutions to this would be x could equal 2 or x could equal negative 2. But as we recall, this means the distance between x and 0 on that number line is 2. And remember, those absolute values are positive. So if I put this on a number line, just like this, remember, that distance from 0 right there, that's what the absolute value equals. It's the distance from 0. What we are going to do today is look at when that equal sign changes to an inequality. The absolute value of x is less than 2 simply means the distance between x and 0 is less than 2. It's less than 2. I'm going to look at this at a number line again. Simple number line. Let's put -3, -2. I'll make this one a little more complete. So the distance between x and 0 is less than 2, meaning you're going to have this right here. The numbers between here are less than 2, not equal to 2, but less than 2. And if we remember back to compound inequalities, section 2.5, the graph of the absolute value of x is less than 2 is the graph of x is greater than -2 and x is less than 2. And if I look at this graph right here, that's exactly what it's showing. X's that are greater than -2 and x's that are less than 2, not including 2. And if we remember back, compound inequality is saying I just take this intersection of these graphs and I can write it as a single inequality. -2 is less than x is less than 2. That's just this graph here. This inequality is simply this. And if I look at it, it makes sense. This right here, if I look at the left side, is saying x is greater than negative 2, or negative 2 is less than x. Now remember, if I order this relation, meaning this x is on the right, I flip it, don't I have that right there? I certainly do. And if I cover this up, I have this right here. This is an and statement. This is an intersection. This is an and statement. Next example, first example, I should say. I'm going to make a note here. When you see a less than symbol, it is and. So if I have this, the absolute value of x plus 7 is less than or equal to 2. You're always going to want to attack these just like you do an absolute value equation. Get the absolute value by itself. There's no numbers out front. There's nothing hanging out off back. The absolute value is by itself. It is a less than symbol, so we need an and statement, which means you would set up two inequalities joined by one. And look at how this and is put together. Look what happens here. This part of the inequality, the x is less than 2. Isn't that this just written without the absolute value? It certainly is. And when I look at this, I notice my sign is flipped and it becomes negative. But we can put it together and write it like this as an and statement. So that's how I'm going to solve these. You're going to make a single compound inequality and statement when that sign is less than. So here's what I have. Negative 2, and I would keep my sign the same. Less than or equal to x plus 7 is less than or equal to 2. And again, I'll just go back to what we had right up here. I have one inequality that is just the absolute value symbols dropped with less than, and then I flip the sign and make it negative. And I realize that this statement, this sign looks the same as this, but isn't it really flipped? Because shouldn't this be ordered with my x on the left? Yeah, it should be. So it actually is flipped, we would say. Set it the and statement up with the negative number here, keep the signs the same, put the positive 2 here, put what's in the absolute value in the middle, and now solve for x, just like we did in compound inequalities. I would subtract 7 from all sides. Negative 9 is less than or equal to x. That goes away, is less than or equal to negative 5. If I go to graph this, here's negative 9, I will say. Negative 5 is here. I'll just say 0 is here. I am concerned with x's that are between or equal to negative 9 and 5. There's my graph, and I got it. Less than and. Set it up like this. I take the negative and put it here. What's in the absolute value, once it's isolated, goes in the middle, and this 2 goes here. But this is why, because a compound inequality, I make 2. Let's look at the next example. This one we got to pay attention to a little bit. And the more you pay attention and the more you figure out what's going on with these, the easier they will be. I could certainly set this up, but it's going to look weird. If I take the same sort of logic I did up here to solve this, I would have 0 here is less than 8x minus 11 is less than 0. You would add 11 to both sides, divide by 8, and I'd get the exact same inequality that wouldn't make much sense. X is between 11/8 and 11/8. If I think about this right here, start looking at these. When you have zeros out here, when you have negative numbers out here, start thinking, is it even possible? What sort of numbers are less than 0? Negative numbers, I hope you're thinking. Can the absolute value of anything be less than 0? Can it be negative? No, it cannot be. It doesn't matter what this x value is here, because the last thing you are going to do once you multiply by 8 and subtract 11 is take the absolute value, which is going to make it positive, which cannot be less than 0. This one is no solution. Why is it no solution? Because the absolute value cannot be less than 0. Next example. Do an easy one, just setting it up. First thing you're going to do, is the absolute value isolated? It is. I see a less than symbol. I don't have any 0. I don't have any negative numbers here. This just needs to be set up and solved. The negative 3.5 goes here, is less than or equal to x, is less than or equal to 3.5. That's it. That's all I got to do. If I went to graph that, I would have negative 3.5 here, 0 would be here, positive 3.5 would be here. You are looking at a closed circle because it's equal to, and you are looking for x's in between here. And you can certainly test it. Test a number that's bigger than 3.5 out here. Well, 5. Is the absolute value of 5 less than 3.5? No, it's not. Then it should be included in my solution set. If I test something smaller than negative 3.5, negative 10, the absolute value of negative 10 is positive 10. Is 10 less than 3.5? No, so it shouldn't be included in my solution set. Pick a number that's in your solution set. Is 0 less than or equal to 3.5? The absolute value of it? Sure it is. That's why it falls in here. 1 less than 3.5. Yes, that's why it's included in there. We will call that A. We'll call that B. Absolute value of x minus 3 is less than negative 1. Again, when you see this negative and you're talking about numbers that are less than negative 1, start thinking to yourself, what's a number less than negative 1? Well, negative 2, negative 3, negative 4, negative whatever. It's going to be to the left of negative 1 on a number line. If I look here and I take the absolute value of something, I don't even care what that something is. The last thing I'm going to do is take the absolute value, which makes it positive. Is a positive number going to be less than negative 1? No, it's not. This is no solution as well. When do you got to look out for those? When you got numbers that are less than 0, numbers that are less than a negative. We are going to solve in graph. Solve in graph. We'll call this C to continue on with the ands. And I've got the absolute value of 2w subtract 1 is less than 11. I would pause the video, give yourself a minute, try to set that up and solve it. Okay. My absolute value is isolated. No numbers out front, no numbers behind. Less than 11, no 0, no negative numbers here. I'm good to set this up. This is a less than, so it's an and statement. Negative 11 would go here. My sign stays the same. 2w minus 1 is in the middle. It's less than 11. I just need to solve this inequality now. I will add 1 to all sides of the inequality. Negative 11 plus 1 is negative 10, is less than 2w, is less than 11 plus 1 is 12. Now I need to divide everything by 2. And that leaves me with over here, I'm going to write it over here, -5 is less than W is less than 12 halves, or 12 divided by 2, which is 6. This is ordered because my negative numbers on the left, my smaller numbers on the left, my arrows are pointing to the left. I'm going to graph it. I'll put -5 here, put 0 here, 6 would be a little farther out. Open circles at 5 and 6, and you are looking for numbers in between. And you can certainly test it. Test 7. Is 7 less than 6? No. And remember, for an and statement, it's got to satisfy both. It's got to be one of these numbers in between it. Less than is and. I always remembered the greater than or. These are ors. And I always remember it as great or. Great or. When I see a greater than sign, this sign flipped, I got to make an or statement. And here's what we do with that. Our steps stay the same, but it's set up just a little differently with ors. Absolute value of x subtract 1 is greater than or equal to 5. Is my absolute value isolated? It is. I look at my sign. This is a great or. It is not going to be an and, it is going to be an or statement. You need to set up 2 separate inequalities. The first one is really easy, just like we did up here. This part of it, I just take what's in the absolute value and leave the sign the same. This one, I make it negative and I flip the sign. I'm going to do the same thing here. First one is going to be, I leave it. I just drop my absolute values. X minus 1 is greater than or equal to 5. Or, I'm going to write you down some little tips here. You need to make it negative, and you need to flip your sign. I'm going to say flip my sign. That's how we handle it. So my second one, x minus 1 stays the same. I flip my sign, so now that greater than becomes less than, and that 5 becomes negative. There's my second inequality. Those are the 2 I need to solve. I solve them independently. I will add 1. X then is greater than or equal to 6. Or I add 1 here. X, that goes away, is less than or equal to -4. I'm going to graph that. Make sure it comes out as an or statement, meaning it should, my arrow should point out. Here's -4, put 0 here, put 6 a little farther out here. X is less than or equal to -4, close circle, where are numbers less than -4 or equal to the left. X is greater than or equal to 6. This would go to the right, and I've got my graph. Great or statements, set them up like that. (10 minus m), absolute value of 10 minus m is greater than or equal to -2. I will tell you this has a special solution. Think about it. if it doesn't matter what m is, I'm always going to take the absolute value last, which means whatever I put in for m is always going to be positive. Isn't a positive number always greater than a negative? It certainly is. This one is all real numbers. There's no value that wouldn't make sense. Or you could say infinitely many solutions, but I am going to say all real numbers. And I'd like to show you why. I'm going to do this problem out right here, saying that I didn't recognize what this was. My first thing that I would do with this is I would leave it the same, right? I'd say 10 minus m is greater than or equal to negative 2, or 10 minus m, I would flip my sign and make that negative 2 a positive 2, the opposite of it, and I would solve these independently, and I'm going to do that. So if I subtract 10, I have negative m is greater than or equal to negative 12. I would have to divide by a negative 1 here, and if I divide by a negative, I flip my sign, so m is less than or equal to a positive 12. Same steps over here. Negative m less than or equal to negative 8. I would divide by a negative 1 again. M is, since I divided by a negative, I flip my sign, greater than positive 8. Now if I go to graph that, something special happens here. Let's say here's 8, here's 12. I want m's that are greater than or equal to 8, which means I would have this. It would go this way. Remember, this is a union. This has to be, in order to be a solution or something that satisfies this inequality, it has to satisfy one or the other. And if I think about it, anything greater than 8, that's going to include everything here, going to the right. If I have less than or equal to 12, it is going to be everything going to the left. When this happens, just need to think about it. Is there any number that won't satisfy this? No, it won't. That's what my graph looks like, but I can tell that from right here. Why does every number work? Because it's always going to be positive, and a positive number is always going to be greater than negative 2. But that's why. Last example. We'll amp it up. These are the types of problems you're going to see more. 4 times the absolute value of 2x minus 5 plus 1 is greater than 21. My absolute value is not even close to being isolated. It's not by itself. Remember, to solve these compound ones, this whole thing is one unknown. We keep this together. We do not distribute that 4. Do not distribute that 4. This is the same thing as solving 4x plus 1 is equal to 21. And you would tell me you would subtract 1, divide by 4. That's the same thing we need to do here. We need to isolate this. This is one big variable. So my steps are to subtract 1. 4 times the absolute value of 2x minus 5, that goes away, is greater than 20. I would then divide by 4. Those divide into each other. I'm left with the absolute value of 2x minus 5 is greater than 5. Now I've got that absolute value isolated. Nothing funny going on here. It's not less than a negative number. It's not less than 0. It's by itself. It's a greater sign. It's an or statement. I set up my 2 inequalities. First one, I'm going to go right up here. First one is going to be I just drop my absolute value signs, keeping my sign the same, or I take what's inside the absolute value, I flip my sign, and I make it negative. Now I'd solve these two independently. Add 5. 2x is greater than 10. I would divide by 2. X is greater than 5. Same thing over here. I would add 5. 2x is less than, that's 0 as well. Please don't tell me that's no solution. 0 divided by anything is just 0. I graph it. Here's 0. We'll just put 5 right here. I want x's that are greater than 5 or x's that are less than 0. That is it. There is several problems to solve. We're going to have a couple of days to work on those, but this will get us started in the right direction. If you're struggling with this, please rewatch the lecture. Please rewrite your notes. Please jump on the Google Meets.